Hello, Namaskar. I am Anil Kumar, Assistant Professor, Department of Physics, Government PG College, Naganath Pokri Chamoli. My topics are Kirchhoff's law, Stefan Boltzmann's law, and Weins law. This topic for BSc third semester physics student. The paper name is Thermal Physics and Statistical Mechanics. And unit number 4, the name of unit is Transport of Heat and Kinetic Theory of Gases. First, I will discuss about Kirchhoff's law. Kirchhoff's law is a very important law for understand black body radiation. The general meaning of the Kirchhoff's law is that if a body is a very good observer of heat, it also be good emitter of heat. This is the basic concept of Kirchhoff's law. Kirchhoff's laws give us a special relation between spectral emissive power E lambda and absorptive power A lambda, so that we should a little bit understanding about spectral emissive power E lambda and absorptive power A lambda to discussion of Kirchhoff's law. Now we will first little introduce spectral emissive power and absorptive power, and then we will study of Kirchhoff's law. Now here I take first a spectral absorptivity is A lambda. Spectral means the radiation we can consider a particular wavelength between lambda to lambda plus d lambda. This is the spectral condition, and the definition of is spectral absorptivity is that it is defined as the fraction of incident energy absorbed per unit surface area per second at wavelength from lambda to lambda plus d lambda. That means the spectral absorptivity is the fraction part, like 1/3, 1/2 of the incident energy which observed by body at per unit surface area in 1 second. Suppose the absorptivity is the 1/3. That means when the incident of radiation on the body, 1/3 will be absorbed. Now here I will take, this is our black body, and we consider this area is the unit area, and now apply to dq amount of radiation. This is the dq is amount of incident radiation, or this is a incident this particular area. There are three possibilities. First, this amount A lambda dot dq will be observed by this body in 1 second. This amount of radiation will be observed, or this is the range of our radiation is the lambda to lambda plus d lambda, so this is called a spectral. Now is the second possibility, the remaining part of the incident radiation will be reflect. This part will be reflect, and same the reflection coefficient is the r lambda, then r lambda dot dq will be amount of reflected radiation. And third possibility, the remaining radiation can be transmitted. This is a transmitted, or suppose T lambda is the coefficient of transmitted, then T lambda dq, the amount of radiation, will be transmitted. Now there is the when dq amount of radiation incident in 1 centimeter square area in 1 second, then A lambda dq will be absorbed, R lambda dq will be reflect, or T lambda dot dq will be transmitted. For example, suppose A lambda is 1 by 3, R lambda reflected fraction also 1 by 3, and transmitted coefficient also to 1 by 3. So this means if the one part of initial amount of radiation which is incident on this area, then 1 by 3 will be absorbed, 1 by 3 will be reflect, and 1 by 3 will be transmitted. So now we can say in equilibrium the sum of absorbed part, reflected part, and transmitted part. This absorbed part, reflected part, and transmitted part should be equal to initial part of the given radiation. So we can write this. This is the absorbed part, this is the reflected part, and this is the transmitted part. And the whole value should be equal to incident radiation is the initial value, that is the dq. Now mathematically dq will be removed to both sides, and we get A lambda R lambda plus T lambda is equal to 1. So this is the relation between absorptivity, reflectivity, and transmittivity for the thermal radiation. Now the special case for the perfect black body. Perfect black body is have a special nature. It always to observe all wavelength radiation, no any radiation be reflected or transmitted. That means R lambda will be 0, no any reflection by perfect black body, T lambda also to 0, and A lambda will be 1. That means all amount of radiation will be absorbed by perfect black body. So this point we should be remember to use for Kirchhoff's law is that the spectral absorptivity of perfect black body A lambda is equal to 1. Now the another thing is the spectral emissive power is the E lambda. The concept of the emission is a virtue of the temperature. If any body have a temperature, so then the body definitely emit the emission towards surrounding. All bodies, those temperature is greater than 0 Kelvin, they all are emit the radiation towards surrounded. So now this is the definition of spectral emissive power is the same. The spectral emissive power of a body is defined as the total radiant energy of particular range of wavelength from lambda to lambda plus d lambda. So say we take a particular wavelength lambda to lambda plus d lambda, so this is called spectral, and area should be considered to 1 centimeter square unit area, at time we consider to 1 second. The amount of emission of radiation CO2 is spectral emissive power, and this its unit is joule per meter square per second. And total amount of emission for to all wavelength, this is 0 to infinity, we can write this, the integral 0 to infinity E dot d lambda. This is the total amount of emission to all for all wavelength, and only E lambda is equal to for a particular range is equal to lambda to lambda plus d lambda. Now here is the another important point is that emissive power of perfect black body represented by E lambda, capital E lambda. Now there are two things. One is absorptive power of perfect black body is 1 and emissive power of perfect black body represented by capital E lambda. These two things we will use for drive of Kirchhoff's law. Now we go to Kirchhoff's law. Now this is the definition of our Kirchhoff's law. It states that the Kirchhoff's law states that the ratio of spectral emissive power to the spectral absorptivity for a particular wavelength is the same for all bodies at the same temperature and is equal to the emissive power of perfect black body at that temperature. And mathematically we write E lambda emissivity or spectral emissive power of this body and over spectral absorptive power of this body. This equal the emissive power, spectral emissive power of perfect black body. So this is the general meaning of Kirchhoff's law definition is, suppose we have two bodies, bodies A and bodies B, and other is we have one perfect black body. If all bodies are in same temperature T, then the ratio of emissivity and absorptivity of body 1 should be equal to the ratio of emissivity and absorptivity of body 2, or these all are equal to the emissive power of perfect black body. This is the Kirchhoff's law, or that is indicate to good observer of the heat, also be good emitter of heat. Now we drive this relation for the Kirchhoff's law. This is the derivation. Now the proof of Kirchhoff's law. Now first we consider thermal radiation in a general black body. The general black body we consider, this is our general black body, and we take 1 centimeter square area per unit surface area. This is our per unit surface area, and this amount of radiation is dq, the range of between lambda to lambda plus d lambda. Each incident at this particular area, then a lambda dq will be absorbed. This will be absorbed, and now the remaining part 1 minus a lambda into dq. Suppose 1/3 part is absorbed, then we have remaining is a 2/3. 1 minus 1/3, that is 2/3. So 1 minus a lambda dq will be remaining, or this remaining part come out in the form of reflection, this is reflection, or transmitted, or both, and we can say the 1 minus a lambda into dq amount of radiation in 1 second out from this body in the form of reflection and transmitted, or both. And the same thing, suppose the spectral emissive power is the E lambda, and due to the temperature this body also to emit the radiation, or this is the amount of emission of the radiation, it will be E lambda dot d lambda. This is the emission. Now in the right hand side, this amount of total radiation outgoing in 1 second from this body, and this is amount of radiation incoming on this body in 1 second. Now same thing I write here. Let us consider a simple black body, and dq is the quantity of the thermal energy between wavelength lambda and lambda plus d lambda incident on unit surface area of black body in 1 second. The quantity of thermal radiation absorbed by surface will be a lambda dot dq, and remaining energy will be 1 minus a lambda dot dq will be either reflected or transmitted. And same thing, suppose emissivity is the E lambda, and the amount of E lambda dot D lambda will be emitted. Now the Hess total energy given out per second per unit surface area is 1 minus A lambda dq, this part reflection and transmitted, and plus E lambda dot D lambda, this part by the emission of the body. So this is the total amount of radiation which outgoing from the unit surface area in 1 second in this black body. Now we can apply to the equilibrium or energy conservation law. So then incoming radiation should be equal to outgoing radiation. Our incoming radiation is the dq, that is a dq, and outgoing is 1 minus A lambda into dq plus E lambda dot D lambda. Now simplify this mathematically, to open the bracket with the multiply, that we find dq is equal to dq minus A lambda dq and E lambda dot D lambda. Then dq to dq cancel out each other by mathematically, and we get A lambda, that is the A lambda dq comes right hand side, and this is remaining in the left hand side, E lambda dot D lambda. This is our equation first. Now again we can consider a thermal radiation in perfect black body. The perfect black body is the same thing, same amount of radiation, same range will be incident on the per unit surface area of this perfect black body, and in this case perfect black body will be observed all amount of radiation. No any amount of radiation will be reflected or will be transmitted. Totally radiation will be absorbed by the nature of perfect black body. So now there is no reflection and no transmission. And if emissivity, we know emissivity or spectral emissive power of perfect black body will be E lambda, capital E lambda, then E lambda dot D lambda is the emission of radiation. So in this case, in the thermal radiation of in perfect black body, outgoing radiation in 1 second only E lambda dot D lambda, this is emission part, and incident part is a totally whole part will be observed by the perfect black body. The same thing we write to here, and we can see this is the same, this is the emissivity of the perfect black body, then E lambda D lambda will be emitted, and here A lambda dot dq is equal to dq. That means observability power of perfect black body is equal to 1. That means total amount of incident radiation will be absorbed. So now apply to same energy conservation or thermal or equilibrium law. Incoming radiation should be equal to outgoing radiation. So now this thing, our incoming is this dq, and this is equal to E lambda dot D lambda. This is our equation number 2. Now put this value of dq from equation number 2 in equation number 1. So then A lambda, here is the D lambda we can consider E lambda dot D lambda is equal to E lambda dot D lambda, and mathematically we simplify this, so we find E lambda upon A lambda is equal to capital E lambda, that is the spectral emissive power, and this is the spectral observability power. That means the ratio of spectral emissive power and spectral observability power will be equal to the spectral emissive power of perfect black body. This is the Kirchhoff's law. Now I will try to understand this, like suppose this is one body, the ratio of emissivity and observability is equal to E1 lambda and A1 lambda. Same we consider second body, the ratio of emissivity and observability is equal to E2 lambda upon A2 lambda. Same is this third body, here is the E3 lambda upon A3 lambda is the ratio of emissivity and observability, and this is the fourth body. Same with the ratio of the emissivity is equal to E4 lambda and observability is equal to 4 lambda. So these are four black bodies. Now, if all bodies are placed with a perfect black body, this is our perfect black body where E lambda is the emissivity. If that all bodies are temperature is the same, this is the T temperature. So then, say to Kirchhoff's law, the ratio of emissivity and observability of body 1 will be equal to the ratio of emissivity and observability of body 2 will equal to the ratio of emissivity and observability of body 3 and equal to the ratio of emissivity and observability of body 4, and these all are equal the emissivity of is perfect black body, because here A lambda will be 1, so that is a 1, only we get to E lambda. So this is our Kirchhoff's law. It is very important for the examination purpose. Now my second topic is the Stefan-Boltzmann law. Stefan-Boltzmann law is a very important law, and here the consider when we have a perfect black body, the temperature is the T. T is the temperature of our black body. Then statement of the Stefans is it states that the rate of emission of radiant energy given out by unit area of a perfect black body is directly proportional to the fourth power of its absolute temperature. So that means E is directly proportional to the fourth power of absolute temperature. This statement given by Stefan, and further this is the action proved by mathematically, thermodynamically and experimentally. And now remove the proportional sign or take a special constant. This is called a sigma. This is called Stefan constant. The value of this constant is 5.67 10 to the power minus 8 watt per meter square per Kelvin to the power 4. But after some time there was understand that if we consider two perfect black body, then what happen if the temperature different of these two perfect black body. So now that we consider, this is our one perfect black body, the temperature is equal to T, or this perfect black body we put inside to another perfect black body, that is the T0. This means this outer perfect black body work as surrounded for the inside perfect black body. So then the previous theory or heat exchange law, the radiation will be emit this perfect black body towards our surrounded T0, and then the loss of the heat. The loss of the heat, or then the modify of the Stefan's law like this. If a black body at absolute temperature T is surrounded by another black body at absolute temperature T0, the net rate of loss of heat energy. The net rate of loss of heat energy, because this inside perfect black body is a high temperature, this is a low temperature, the radiation will go to from high to low, then emit or the loss of the heat. Per unit area of the surface, this surface will be E proportional to the T to the power 4 and minus T0 to the power 4. Here T is greater than to T0. And same, we remove the proportional sign and take a constant. So this is a Boltzmann constant. Or this statement is called Stefan-Boltzmann law. Because Stefan's law in 1884 proved by the Boltzmann give a theoretical proof of Stefan's law on the basis of thermodynamics. Thermodynamics, that means when the thermal radiation we put inside the enclosure is like a same of the gas molecules in the enclosure. So then we can apply to here thermodynamic concept to understand of the radiation inside any enclosure. So this is accordance with the previous theory of the heat exchange. The previous theory is the same. Say all body will be emit to radiation towards the surrounded. Now I will try to prove this law. So now this is the derivation of Stefan Boltzmann's law. It is considered that a thermal radiation inside the enclosure like the gas molecules then can be used of thermodynamics concept to study of the radiation. So now here is the clear that when we take a radiation inside our cylinder or enclosure, it is the same as the gas molecules of inside a cylinder or enclosure. So that here we can apply to easily the thermodynamic relation and we will be proved. So we know that this is our first law of thermodynamics, that is del Q is equal to del U plus P dot dV. Given heat is equal to change of internal energy and plus work done. Now also we know that the Maxwell thermodynamic second equation for thermodynamic potential, and that is change of entropy with respect to the volume at constant temperature, which will be equal the change of pressure with respect to the temperature at constant volume. This is our second Maxwell thermodynamic equation. And also we have second law of thermodynamics. This is del S upon equal to del Q upon T, that is change of entropy, and this is the amount of heat, and this is absolute temperature. So now from this equation we can put the value of del S equal to del Q upon del T in Maxwell's second equation. So then we get del Q over del V at T. In the place of del S we place del Q over del T, and this T will comes on the multiplication, T come here, and T del P over del T at V. And again put the value of del Q from first relation of thermodynamics, del Q equal to del U plus P into dV. We put here del U plus P dV upon dV at constant T is equal to T del P over del T at V. Now divide to each term by del V and simplify. So we get first term del U over del V at constant T, and second term del V to divide by del V, and we remaining only capital P. There is a pressure P, and this P is come on the right hand side. We will write minus P, and this is the same right T del P over del T at V. This is our first equation. When we study of thermal radiation, we get a important relation. Important relation is what will be pressure of radiation. The pressure of radiation P always equal to the 1/3 of energy density. Here U is equal to energy density we consider. The U is energy density, and upon 3 U upon 3 is the pressure of radiation. This, and second, total energy or total internal energy of radiation in inside the enclosure will be this U. U is the energy density. Energy density we multiply to the volume, total volume, then energy density and multiplication of the volume, this get to the total energy or total internal energy of the radiation. Now there are two relations. Now this relation we will differentiation with respect to the volume, then we get del U over del V at constant temperature T is equal to small u, and same del P over del T at constant volume V, that will be 1/3 del U over del T with respect to temperature at constant volume V. Now the value of del U over del V at T and del P over del T at V input in equation number 1. Then we get small u is 1/3 T del U over del T at constant volume V minus U by 3 minus u by 3 comes on the left hand side, it becomes the positive, and the addition by mathematically, and it will become 4u upon over 3 equal 1 by third t del u over del t at constant volume v. Then mathematically 3 to 3 cancel out, and rearranging this equation, we can write del u upon u is equal to 4 into delta t upon t. This relation. Now the integral of this relation same as the del u over u will be log u, and del t over log t, and this is a 4, and plus the integration constant. Now take antilog and simplify, that is a u, and we take a constant k, constant is a k, and 4 go to t to the power 4, properties of the log, and we can write u is equal to k t to the power 4, where k is the constant. But also we know that the energy density of the radiation also to equal to the total emission of the radiation at particular unit area. So this is also the total rate of emission per unit area of a black body is proportional to the energy density. That means E is the directly proportional to the U. The E is the here emission rate per unit time per unit area, and U is the energy density. So U is the proportional to t to the power 4. That means E is directly proportional t to the power 4. Again remove the proportional sign and take a constant sigma, or this is E is equal to sigma t to the power 4 is Stefan Boltzmann's law, and sigma is the Stefan constant. Now here we prove the Stefan Boltzmann law by thermodynamically. There is a very simple. We take first equation of thermodynamic. Now second we use the Maxwell thermodynamics second equation. Now third we use the second law of thermodynamics. First law of thermodynamics, Maxwell thermodynamics second equation, and second law of thermodynamics we will be used to drive for this relation. Now my next topic is the Weins law. This is also the very important law for study of black body radiation. Weins law we classified in the three part. One is the Weins displacement law, second is Weins fifth power law, and third is the Weins distribution law. Now we will discuss one to one. First we discuss of the Weins displacement law. Weins displacement law is the very simple. This law is define the inverse relation between temperature of black body and wavelength at which maximum radiation will be emitted. The inverse relation, that means when temperature will be increased, wavelength will be decreased, or wavelength is increased, temperature will be decreased. But the wavelength at a particular point wavelength where emission is the maximum at any absolute temperature, and it states that the wavelength of maximum radiation shifted, wavelength shifted to shorter, shift करेगी shorter की ओर with increase the temperature, when we increase the temperature. So this statement so we call displacement law, because wavelength is a shift towards shorter, and we can write lambda m is directly proportional to the 1 upon T, or inversely proportional to temperature. Now this we can say in the experimentally result. This is a black body radiation graph. So we can say very easily at 2000 Kelvin the start to radiation is the emission power, and this is a particular point where emission is the maximum. So this is the maximum point of emission radiation. This point have consider the wavelength. This wavelength is a lambda m. This is called a lambda m, and a wavelength at a particular point where maximum radiation will be emitted. So we see at 2000 Kelvin our wavelength is, lambda is here, this point, 1, 1.1, 1.2, approx to 1.2. When we increase the temperature 2000 Kelvin to 3000 Kelvin, we see that this is a graph of emission. It will go to increase. At this point reach, this is the value of the maximum emission. Or now we draw the downward line, so we find this value of this time is our wavelength. Now wavelength is approximately 0.9 according to this graph. That means wavelength is shifted shorter. Wavelength will be decreased when we increase the temperature 2000 to 3000, and same process to again when we increase temperature the 4000 Kelvin. So this peak value we get to this point, and if we draw the vertical downward, so we point to this point again to the decrease the wavelength. That means wavelength is shorter to shift to shorter, or this is Weins displacement law. Now second is Weins fifth power law. Also the Weins is assume or prove that these point where the emission is the maximum emission of the body is always directly proportional to the fifth power of temperature. This is the Weins fifth power law. It will be proved in this lecture in this topic. Now third is the Weins distribution law, and further we combined this lesson and this lesson. So then we get a third lesson, which is show the and give our energy density, and this is the energy density at particular range lambda and lambda plus d lambda. It will be A upon lambda to the power 5 from this relation lambda to our power 5 into e to the power minus b upon lambda t into d lambda. So this relation is called Weins distribution law. Now let we start to the drive our Weins displacement law by the theoretically. So this is the derivation of the Weins displacement law first. Now same thing here, let us consider a cylinder whose walls as well as the face of the piston are the perpetually reflecting and elastic. Weins is the consider radiation filling in the enclosure as electromagnetic wave. This is the assumption of the Weins. When we filling the radiation inside the enclosure, it behave like electromagnetic wave. That means the speed of radiation inside the enclosure will be equal to the speed of electromagnetic wave, that is equal to c, and allow the slowly adiabatic expansion. Or this our mechanics we apply to allow the slowly adiabatic expansion. Here are the two things for the proof of Weins displacement law. One thing, the radiation is considered as the electromagnetic wave with the speed of the c, and second thing, allow adiabatic expansion. Now for the calculation we can consider our enclosure is the spherical. So that is we consider our spherical enclosure and whose walls move at uniform speed nu. The walls of this spherical enclosure also to move with a new velocity or frequency, and thermal radiation will also to move with the speed of the light c, and wavelength is the lambda. So now there is a small p is the pressure of this radiation and u is the energy density. So now inside of this enclosure there are two things. One is the walls of this enclosure is the move with the velocity, and second is radiation also to move inside with the velocity c, then what they are develop here Doppler effect. Now Doppler effect, change of the frequency for observer or source, and frequency is also the function of the wavelength. So we can consider that due to the Doppler effect, change of the wavelength. So now we can see due to the Doppler effects, radiation wave incident on the wall at angle theta. So when our radiation are incident on this wall angle theta, the change of the wavelength d lambda will be 2 nu cos theta upon c into lambda. This expression for the use of Doppler effect relation, we will find this. Now again see, this is our center, and now this here start our radiation and incident at this point. This point is the capital A in the I will show the later. Now start to reflect this point and radiation go to here, and incident this point is the B, again to reflect from here and go upward. Now there are two successive reflection from here to here. The distance, the radius is the r, or angle of incidence is the theta. So that is distance r. So its distance will be r cos theta from here to here. Same this triangle also the r cos theta. That is the total distance from this point to this point is 2r cos theta. This is 2r cos theta. This is point A. This is a point B. So now we can see two successive reflection at A to B in the figure. The wave travel distance 2r cos theta. That means the number of reflection per second will be the total number of reflection the 1 second inside the enclosure. It will be the speed of radiation, that is a c, upon distance, that is a 2r cos theta. The c upon 2r cos theta is the number of reflection in 1 second. Suppose we take a time dt, then total number of reflection will be c upon 2r cos theta into dt. This is the 1 second. This, when we multiply by dt, it will be total number of reflection in the dt time. So this is the number of reflection in the dt time. That means the change in the wavelength in dt time will be d lambda is equal to 2 nu cos theta upon c into lambda. This value will multiply of the total number of reflection at the time dt. It will be c upon 2r cos theta dot dt. Now the cos theta to cos theta the cancel out each other, and c to c divided, and simplify you can write d lambda upon lambda is equal to nu dt over r. Now the nu is the velocity, or r is the displacement or the radius of this enclosure. So then nu should be dr over dt. This is dr over dt. So dr is equal to nu into dt. So we can put the place of the nu into dt as a dr. So we get d lambda over lambda is equal to dr upon r. Now this relation we get, and now we will integral both sides. So we find that is the left hand side is the log lambda plus log r and plus log c, and taking anti-log, and we can write that is the lambda is equal to, this is the property of the log, this is the plus will be to multiple, that is the rc. That indicates the lambda is directly proportional to the r. This is a very important relation. The wavelength of the radiation inside enclosure is directly proportional to the radius of enclosure, or we can write in the form lambda upon r is equal to c, the constant. Now again here we are allowed to slowly adiabatic expansion. So we know that the adiabatic expansion relation is T PV power 1 by 3 is equal to constant in the terms of temperature and of volume. So this is our T V to the power 1 by 3, and also we know that V is equal to 4 upon 3 pi r. This is the formula of the volume of the spherical bodies, and put the V is equal to here, we see 4 upon 3 pi also we will take a constant form, and R3 go to 1 by 3, that is the R, that is TR is equal to constant. So now we are compare from equation number 1 equation number 2. Here lambda upon R is equal to constant, here T upon R is equal to constant. That means lambda and R have a inversely relation, or we will write lambda into T is equal to constant, or represent is the lambda is inversely proportional to the absolute temperature T, or this is the expression for Weins displacement law. Now after that we will derive the Weins fifth power law. And fifth power law is also the very simple. Same we consider to here an isolated radiation wave of wavelength lying the wavelength lambda plus d lambda in the spherical enclosure, and allow the alone or undergoes adiabatic extension. The spectral energy density, the wavelength and width of wavelength band will be changed inside the radiation. Now there we apply to the first law of thermodynamics. Then first law of thermodynamics is equal to a change of internal energy du plus work done, that is a P dV is equal to dq, but dq will be 0 because here is the adiabatic expansion, that is dq will be 0, so we consider to 0, and u we can write in the form of the lambda d lambda, so that is the u lambda that d lambda. This is the total internal energy of the radiation at a particular wavelength range is equal to lambda plus d lambda. Now again we know that total energy of the radiation will be energy density will multiply with the volume, u lambda into V, and also you know that pressure of radiation will be 1/3 of energy density, so 1 upon 3 energy density we have u lambda d lambda. Now put this value in this equation, above equation, so that we can write d u lambda into V d lambda. Capital in place of capital U we will write small u lambda V and d lambda, and 1/3 here P, in the place of the P we write 1/3 u lambda d lambda into dV. So now in this equation u lambda d lambda we consider the 1 first, or V we consider to second, and apply to the conditional differentiation of the multiply, so that will be differentiation of the first, and d over u lambda dot d lambda, and second remain same. Now plus first remain the same, u lambda d lambda is same, and differentiation of the second dV, and that will be right same 1 upon 3 u lambda d lambda dV is equal to 0. Now these are the same values. This is 1/3 and plus 1, that will become to 4/3, that is 4/3 u lambda d lambda dV is equal to 0. Now the divide to both sides u lambda d lambda, so here is it becomes d u lambda d lambda upon u lambda d lambda, and it's become equal to 4 upon 3 dV, and also the V come on the divided in the left hand side, so we can write minus 4 upon 3 dV over V. Again a volume is equal to 4 upon 3 pi r cube, and then dV upon V is equal to dr upon r, dV upon dr upon dV. So that here we can write 4 upon 3 dV upon r is equal to minus 4 dr upon r, also come here to 1/3. So these values now we will integral, so d over u lambda d lambda upon u lambda d lambda will be integral, it becomes log u lambda d lambda, same thing integral upon dr upon r, then 4 multiply of the log r and equal to log c. This is again the integral constant. Now take a antilog, it becomes u lambda d lambda, and multiply of this log, remove log, and this 4 to go to power of the r, become r to the power 4 is equal to constant. But also you know that the lambda is directly proportional to r, This we discussed in previous. So that d lambda is equal to dr, we can put the value of d lambda is equal to dr at this equation. This equation become u lambda r to the power 4 into dr is equal to constant. Now again we integral of this equation, it's become u lambda r to the power 5 is equal to constant, but tr also the constant, tr is equal to constant. Before previous topic, previous point we have discussed. So tr is equal to constant and u r to the power 5 is equal to constant. That is means t comes r is equal to constant upon t. T comes in the minus t to the power minus 5. So we can write this u lambda t to the power minus 5 is equal to constant. When put the value is equal to t into r is equal to constant upon t. So this is the formula of temperature and energy density. But also we know that the temperature and wavelength are inversely relation, that is lambda m is inversely proportional to t. If t is the minus, so lambda will be plus u lambda plus lambda power 5 is equal to constant. Again also we know that the energy density is equal to the total amount of emission per unit surface area of perfect black body. So this is, we know that spectral radiancy E lambda is directly proportional to the energy density U lambda. So we can put here in place of U lambda is equal to E lambda. This is the emissive power into lambda to the power 5 is equal to constant, or E lambda is equal to T to the power minus 5 is equal to constant, or E lambda is directly proportional to the fifth power of temperature. At a fifth power of temperature. So this is the derivation is proved for Weins fifth power law. Now third one and last we have Weins distribution law. This is the very simple. We take a first relation of Weins. This is the Weins displacement law. The lambda t is equal to constant, and second is Weins fifth power law. U lambda to the power 5 is equal to constant. Now we combined these two relations. So this equation we can write to here. U lambda and lambda to the power 5 go to right hand side in the divide. We take in the divide form and multiply both sides d lambda and d lambda. Now this have a constant. This in the place of this constant we take a this constant, but lambda t is also the constant, so we have put the function of lambda t. This is the indicator of the constant into d lambda. So this is the where capital A is a constant and is an undetermined function of the product. This is the most common way of expression of the Wein distribution law. So this is the Wein distribution law for in form of one constant A. But some examination to ask the Wein's distribution formula in terms of the two determined coefficient A and B. So then Weins also assume that the radiation inside the enclosure is produced by some kind of resonator. Again, the Weins is also to assume the inside of enclosure the radiation is also work as a resonator. A resonator have the frequency, or this frequency is the directly proportional to the kinetic energy of the radiation. The kinetic energy of the it will be half mv square, or that will be equal to AC upon lambda. This is our assumption of Weins. When the consider of the radiation like a resonator inside the enclosure, then we can apply to here Maxwell-Boltzmann distribution law, and Maxwell-Boltzmann distribution law give us a number of resonators, that is the n lambda, that is the range of lambda, have a number of resonator that will be equal to phi dash lambda e to the power minus AC upon lambda, AC upon lambda, that is the energy form, into K into T, where is the K is the Boltzmann constant. Now again you take another constant, is AC upon K. AC upon K, AC upon K, these are all constant. That becomes the new constant, that is the B, AC upon AK, and this equation we can write this form phi dash lambda e to the power, that is become minus B into lambda T. But the total number of resonator also the directly proportional to the energy density. Energy density, total amount of energy 1 centimeter cube volume, or n lambda is also the volume, is the consider the number of resonator. So the number of total resonator is equal to the spectral energy density is the wavelength interval lambda to lambda plus d lambda may taken is a proportional to the n lambda. That is means the energy density is equal to the number of resonator. So we can put here u lambda d lambda is equal to phi dash lambda e to the power minus b lambda dot dt. Now compare of this equation from the general equation. So here we become psi dash lambda is equal to a upon 5, and function lambda t, that is function lambda t is equal to minus b upon lambda t. Now put these values in this equation. So we will write this u lambda d lambda a upon lambda to the power 5 e to the power minus b upon lambda t into d lambda. So this is the Weins distribution law with two constant a and b. These Weins distribution formula with two undetermined constant. In the examination, if you ask the one undetermined coefficient relation of Weins distribution formula, you will be right u lambda d lambda a upon 5 function lambda t into d lambda by combine these two relations. But if I ask the Weins distribution law in the form of two coefficient, then we will write u lambda d lambda is equal to a upon lambda to the power 5 e minus b lambda t into d lambda. Now this is the proof of three laws of the Weins distribution displacement law, means fifth power law and Weins distribution law. We prove here the Weins distribution law is the very important law for the black body radiation and give us a very experimental result. But there have some limitation of the Weins distribution law, because the Weins distribution law is the failure to study of a longer wavelength. Now there are the completed of three topics: Kirchhoff's law, Stefan-Boltzmann law, and Weins law in the theories, concept, and all derivation. So thank you.